Okay, so hello everyone. This is the 10th to 12th session on and finite element modeling of welding processes. I'm Zia Krishan author at TA and PMRF TA for this course. So today would be we're having a short discussion, and uh, so we'll deal with fundamentals of we'll review the fundamentals of metal transfer in arc welding and FE based modeling approaches. So these are the topics which were discussed in the 10th week. And I would also be doing some sample problems. So let's just go back to the notes which was discussed in this current in the 10th week of this course. So we started with say metal transfer in arc welding. So the different types such as GMAW, which is gas metal arc welding, then SMAW, SAW, and GTAW. So GMAW has been used to develop low-cost 3D metal printer, and in GMAW there are two different modes of metal transfer. One in which we have this what we call as the continuous mode, which is the and the other is the pulse mode. So in continuous mode, so the metal transfer takes continuously, as is evident from its name. And in the pulse mode, the metal deposition takes place in uh, say one drop at a time, something of that sort. Yeah. So in GMAW, the CMT, which is cold metal transfer, it is the new form of gas metal arc welding, and it's not exactly cold. It is in lower temperature than regular GMAW process. Now the modes of metal transfer, which is we start with GMAW. So in this case, there is transfer of molten metal from consumable electrode to the weld pool, and there is current, voltage, or gap. Secondary factors that we have are the shielding gas, which yeah, shielding gas is essentially used to say stop certain chemical reactions from taking place. And then we have this composition of electrode also influences metal transfer, the diameter of the electrode. Now there are different types of metal transfer. We start with the short circuit transfer, the globular transfer, and spray transfer, right? So in globular transfer, what happens is the welding current is low, and which is more than the short circuit transfer, and R gap is large. Droplet can grow slowly, and the droplets continues to grow until gravitational force exceeds the surface tension force. And as soon as the drops attains a large size enough, gravitational force becomes more than other drop holding forces, and drop separates from electrode tip and it's transferred to the weld pool, right? That is what happens in globular transfer. Means the transfer will take place in forms of globules. The melted metal will drop off, and the droplet transfer occurs when it attains size which is larger than the electrode diameter, right? Then we come to spray transfer. In spray transfer, welding current density is higher than globular transfer, and high welding current density results in high melting rate and greater pinch force. Then droplets are formed rapidly and pinched off quickly by high pinch force. The droplets are of very small in size, and then high welding current increases temperature that lowers the surface tension force, and it also decreases the resistance to detachment of drops. Okay, then we come to short circuit transfer. In short circuit transfer, a low welding current is applied, because of which droplet grows slowly, and when drop touches the weld pool, short circuiting takes place, right? So this happens in this segment here. So in this case, current keeps on gradually decreases, and then during short circuiting, there is an avalanche of current flow, right, till it reaches its peak. So this is where the short circuiting ends, and then we have this arc phase. So due to narrowed arc gap, molten drop does not attain a size big enough to fall under gravitational force. After short circuit, welding current flow increases abruptly and results in excessive heat generation. The molten metal of droplet becomes thinner, low surface tension. So arc, so, and the molten metal is transferred to the weld pool. An arc gap is established that increases arc voltage abruptly. So here what happens, we started with arc, then there is short circuit. So in this case, short circuit pinch and finally reignites arc and the flow of current starts. And this keeps on repeating. Essentially. Now, continuing along this line, so the short circuit in GMAW is characterized by the regular contact of liquid metal drop attached to the electrode tip to the weld pool, and an alternation of arc and short circuit periods that are unique among the metal transfer modes, usually in GMAW, and a new arc period initiates when the liquid contact between the pool and the electrode is shaken, and the frequency with which the current touches the melting pool varies in a range of 20 to 200 times per second, right? So this is the frequency in which the electrode will keep on touch the melting pool. So it's 20 to 200 hertz. And the molten metal tends to be transferred to the melt pool mainly by the forces of magnetic origin and surface tension. The modes of metal transfer is we let's discuss about the pulse spray transfer. In pulse spray transfer, the power supply is designed between a high spray transfer, right? High spray transfer current and a background current and a low background current, isn't it? So and it allows supercooling of the weld pool during the background cycle, and it's different from the true spray transfer. So in each cycle, one droplet transfers from the electrode to the weld pool, and it's suitable to weld out of poison thick section because of low background current with higher energy than the short circuit transfer. And finally, it produces higher average current and improved sidewall fusion. So these are the features of the pulse spray transfer. And in cold metal transfer, it's actually a part of GMAW. And in principle, it works at reduced welding current and retracting the welds wire at a short circuit condition. And it ensures a drop by drop deposit of weld material. And it was first developed for thin materials with strict control of weld parameters. So nowadays, the welding of dissimilar metals and thicker materials, along with the improved weld-based bead aesthetics, are developed. It's one of the important options of metal printing technology development. And CMT process is developed by Fronius of Australia in 2004. So this process differs from GMAW in terms of mechanical droplet detaching method. So how does the CMT differ from GMAW process? So the main difference which happens is in terms of which wire, the way that we use wire to feed the weld pool. So in GMAW, the wire is continuously pushed forward into the weld pool, right? And in CMT, wire is retracted. It's retracted the moment when the instant current flows. Right, so when the say current starts flowing, then the wire is retracted, and then here it breaks the arc, and the metal detaches from the filler. Droplet detaches from the filler, and then it will fuse with the still molten base metal. Again, what happens is the wire will move forward to create another arc, and all this phenomena happens several times in each second. So it's a very repetitive process. So CMT provides a controlled method of material deposition by sophisticated wire feed system at low thermal input. In effect, it needs high-speed digital control technology, right? And in the cold metal transfer, so the main features of the CMT process are Short circuit occurs with low current contributing to low heat input. And the so the short circuit occurs in a stable control manner, and during the metal transfer, the current drops to near zero, right? Uh, and thereby any spatter generation is avoided. And as soon as the metal transfer is completed, the arc is reignited and the wire is fed forward once more with the welding current flow. And in the then CMT welding, the cycle, this electrical signal cycle, it consists of three phases. The first phase is the peak current. In its case, the constant arc voltage corresponding with high pulse current happens. And in this case, the ignition of the welding arc takes place easily and it forms droplets. In the background current, there is lower current level, prevents the globular transfer of little liquid droplet, and continues until short circuiting occurs. And in short circuiting, the arc voltage is zero, because that's the reason we see a sudden increase in the current flow, and the wire is given back drawing force. Liquid fracture occurs, and then there will be transfer of metal into the welding pool. So it's in the short circuiting phase when that just after shop that uh, when the separation of metal droplet from the filler, or the filler droplet drops off and then falls into the welding pool. So schematically, now let's take a look at how does metal transfer in SAW occur. So we have this AC power source. So in this case, there is a two-wire tandem SAW process. So we have two arcs, one and the first and the second arcs, first arc and the second arc, and they are independently controlled. Right, they will be independently controlled by two different power sources. One power source is a DC power source, the other one is the AC power source. And then the so this lead wire is melted and then it joins the pool. Likewise in this likewise in trail wire again, which is in this case is powered by an AC power source. So this is the second arc which will be created here. And then here happens to be that flux hopper. So flux is provided through this mechanism, right? And in the one advantage that it offers high deposition rate, and it has applications in shipbuilding, pipelines, and infrastructures, all of which require high deposition rate. And how do we have this effect, wave control trailing arc on penetration? So we start with, say, the vertical axis has current, voltage, or power, and the horizontal axis is time. So we start with say positive current level implies that there is some penetration going on, and the negative current level implies deposition, right? So the balance will be decided based on the stretch, or so to speak, the area of which this curve, the square curve, or sorry, the rectangle curve makes with the time axis. So if the integration of this region is higher than that of, say, green region is higher than that of the dark gray region, that it implies that the cycle is in the favor of penetration, right? So yeah, so control penetration and bead with independently for the same heat input. Now let's come to metal deposition rate. So this is the relation between, say, which material we are using as filler material, right? Which is as filler, and what is the area of the cross section of that wire. Okay, and then eta is the efficiency of the solid wire efficiency, and F is the feed rate. So how much feed rate that we are having, right, of electrode? How much is it being transferred to the whirlpool? So that m dot gives us the deposition metal deposition rate for that welding process. Yeah. So we have, so as we know that there are three different ways: globular transfer, short circuit transfer, and spray transfer. And the parameters or the power source that we have is these also affects this welding process. Right now, as we come to the second aspect of our discussion, the second part of our discussion, which is the FE based modeling. So what we do is say we have this filler material and then this wire feed, then we have this molten droplet. It drops off because of this creation of arc between the workpiece and the filler material. So when this droplet, as it becomes larger than the wire diameter, it will drop off and then join this weld pool. And for the symmetric, let's consider, let's assume this mechanism to this configuration to be symmetric. And the holding force can be, say, electromagnetic force, like gravitational force, or plasma drive force. And the mathematical criterion for the transition from globular to spray type metal transfer as a function of welding current, isn't it? Now let's come to how do we model it, right? So for the computational domain, we are only choosing one molten droplet and then the region till the workpiece. So we can divide this this computational domain into two subdomains. Subdomain one is where the liquid solid interface. So it's just okay. So what we do is we actually divide into two segments. So we come from here, the one after just before the droplet drops off, and the other part in the subdomain in this computational domain will be where the droplet is under electromagnetic field, shielding gas and plasma arc and gravitational field. So these are the so this is the ambient, so to speak, the environment of the falling droplet. So we have divided this computational domain into two aspects. Okay, and then yeah. Okay, so domain has to fix first, then we'll say in this computational domain 2. So in the computational domain 2, we'll take part, we'll take this aspect. So that once the drop joins the whirlpool, right? So there will be some boundary interaction between the plasma region and this solid workpiece. Then we have this addition of liquid droplet going into the picture. We have this boundary interaction. And so this is a more detailed schematic of the problem here. So only heat transfer is only passed on to the wire so that it is able to melt and form this molten droplet. Okay, and then the electromagnetic field we apply. There is a constant wire feed rate. So this formation of electric arc, then it just drops off. There is the heat transfer material flow and drop interaction with molten pool, solution domain, workpiece, then only heat transfer, symmetric, right? So the problem is symmetric and yeah. So in this region, what happens is when the droplet drops and joins the whirlpool, then we have heat transfer and material flow is also taking place as it drops, right? So there is a formation of electric arc, as you can clearly see. Now we come to the governing question. So we would be solving the Navier-Stokes equation, and since our material is assumed to be uh, incompressible, so that's the reason we have mass continuity equation. This is the divergence of rho into v vector is equal to 0, and the momentum conservation equation is This is what, so there is no transient term. Even in the mass quantity term, we can say that we are doing some uh, simulation. We are approaching, we are assuming our problem to be steady state in nature. So that's the reason. So I should not tell that it's as of now incomplete. It's just that partial rho by partial t happens to be 0. And for a momentum conservation equation, that is what happens. Then we have this energy conservation equation. So divergence of rho v minus capital V into h. So h is our enthalpy, right? And this is equal to J square by sigma. So J is the current density and sigma is the electrical conductivity plus divergence of K by Cp. So kappa or K will be thermal conductivity divided by Cp is the specific heat constant. Grad of H is essentially the gradient of enthalpy. Then minus of 5 kb by kb is the Boltzmann's constant and E is the electronic charge. Cp is again the coefficient of the specific heat at constant pressure. Now J vector dot grad of H. J is the current density and H is, as we know, it's the enthalpy minus U. So U is the radiative emission coefficient. And this was for the same mechanical aspects. Now we come to the electric and electromagnetic aspects. So we first have this current continuity equation, which is the thing by divergence of sigma of grad of phi is equal to 0. And the current density J is related to the electric potential phi by J is equal to minus sigma grad phi. Right. So, and we have electrical conductivity sigma. J is current density. And then we have electric potential phi, magnetic field strength V, and magnetic vector A, potential A, right? So current density J is related to electric potential phi by J vector is equal to minus sigma grad phi. B vector is the magnetic field strength, or we also call it magnetic flux density, and this is equal to the curl of A vector, and A vector happens to be our magnetic vector potential. So Laplacian of A vector is equal to minus mu naught into J. So mu naught here is the permeability of free space. And then we also have to take into account the effect of free pressure and the surface tension. As for the modeling approach, the summary is that the computational domain is divided into arc domain. So arc domain consists of arc column and then the shielding gas, and metal domain will comprise of electrode, detached droplet, the workpiece. So that's how we had defined our computational domain. One into arc domain, which is arc column plus shielding gas, and the other one is and metal domain, which essentially consists of electrode and detached droplet and workpiece. Now, for a current distribution, the current continuity and magnetic field equations are solved in the entire computational domain, right? So the primary variables, including P, U, V, and T, are calculated separately in the metal domain and in the arc domain. So in the metal domain, the arc region is considered as void. Right? So, and two domains are coupled through interfacial boundary conditions. So that is essentially to ensure continuity of. So we'll have to prescribe some at interface. There will be some interactions going on between both the domains. So, yeah, so we may require continuity or in certain components of certain values, certain physical values. So it should say deal with temperature distribution and also with respect, yeah. So the volume of fluid method is solved in the metal domain to track the moving free surface of the electrode. Right? Droplet and weld pool with free boundary conditions which are set at the metal surface. So this is the revision part of the review. It was, there is not much to be covered in the 10th week. So what should we do is, let's take an expression here. Let's look at this expression. And I'll just take a screenshot because we will be so using this equation, right, in our some solved examples. So let me copy and go back to the presentation. So just paste it here, right? So we'll be solving a question like this. So it's a cube of length 100 mm needs to be additively manufactured, right? So a mild steel electrode with a diameter of 10 mm is feed with a rate of 10 mm per minute. So the density of mild steel is assumed to be 7,000 kg per meter cubed. Now, assuming the efficiency of the process to be 1, calculate the deposition rate. So this is what we are trying to do here. So what are we given? We are given that the diameter of the mild steel electrode is given. It's then using which we can compute A, and it's fed at the rate of 10 mm per minute. So it will be F. F is the 10 mm per minute, which can be converted into 10, say, right? So we have to convert it to meter per second. So then the density of the mild steel is assumed to be 7,000 kg per meter cubed. So either to have consistency of certain values, we can let's convert things into, say, this density itself into, say, some sort of an mm representation, right? So it will be, first let me make it superscript here. So superscript. So, yeah. Now what we do is, let me insert one text box. Okay, so row, and I'll be using one insert some symbols. So what I'll do is, let me see if there is any function here. We insert as we have row here. So row equal to, uh, 7,000, right? So row will be equal to 7,000 kg per meter cube. This is what we are given. Yeah, meter cubed. Right? So with this, we are able to have it as, and then we know that 1 meter is equal to 10,000, sorry, 1,000 mm. So what we'll have is, we'll have 7,000 divided by 10 to the power 10 per 9, right? We'll have 10 to the power 9. So then we'll have 10 to the power 9 kg divided by mm. mm cubed, isn't it? So this is what, so this eventually gives rise to this will be 7 into 10 power minus 6, right? kg per m cubed. Right? So this is our rho. Now we come to A. So A will be how much? A will be pi into d, which is diameter squared by 4. I'm just using this here because yeah, so this will be 3.1415 into 100 because d square is 100 divided by 4. So this comes out to be how much? It will come out to be 3.1415 into 25, right? So I'll just do it. 3.1415 into 25, right? So it's 78.5375. So this will be mm squared. So with this we have A and F is we are given as 10 mm, 10 mm per minute, right? Yeah. So now we are, and then eta is also given as insert say symbol. We're looking for eta. So let's see, where is eta? Um, So why don't I just write this? Let's take just this to beta as of now. That's close. So eta is equal to 1, right? So now we can compute m dot. Let me just write is m dot. So eta is 1, and then rho is 7 into 10 power minus 6. And this is in kg. Right, and then so I'll just so it's 10 power minus 6. Right? So it seems that it all happens to be in superscript. So let me just I'll convert this into superscript, right? Okay, so then we have A is 75 to this much, and F is 10. So we'll have 7 into 7 at one, this one then. So this into 7. So it's 549.76 into this will be 10 power minus 5. Right, and then in scientific format, we can write this to be 5.49 and then multiplied with 10 power minus 3. Right, so this will be kg per minute, isn't it? So this we can say 10 power minus 3 kg is gram, right? So we have 5.49 gram per minute. So this will be our deposition rate of the filler material to the weld pool. Yeah, so there was just one question in this regard because it seems just one of them required some numerical solution, some calculative, some simple formula based question answer. Then apart from that, I think now say in current continuity equation, I just give a view, right? So many a time or in general electrodynamics, many of the equations, it will look similar to, at least for the mass continuity equation, they look very similar, isn't it, the expression wise? And when we take a look that grad of phi happens to be electric, and phi is electric potential, and grad of phi is what we call as electric field. So it is divergence of divergence of J is equal to 0. So that is what is the charge continuity, current continuity equation in electromagnetism. And in not all these cases, what we had assumed is the steady state transfer, steady state behavior taking place, isn't it? So, and in general, say for problems when we have even time dependence, then we have to come up with another expression, or we have to use the transient equations to solve such problems. And yeah, so I think pretty much this is what is there in the 10th week of this course. So for that, I had talked about something to discuss about Phoenix. So as of now, still will actually write code in our extra sessions that we'll have just to get a hang of. And this happens to be a very nice resource on to learn Phoenix, which is an open source package for doing finite element modeling. And there are certain very good tutorials on this for using this software or this software package called Phoenix. So one of the examples that we had started last time was the transient elastodynamics with Newmark time integration. So that's what is essentially the goal here. So what we would have liked essentially is to code it up. So what we do is, why not do it in the upcoming extra session that we have? And if anyone is interested, you would always please do. It's a very nice package to learn, and otherwise we can always discuss it. If you can just message me or just comment it on the YouTube video underneath the YouTube video. So that is pretty much what we're supposed to discuss. So let me just stop sharing my screen and then. Yeah, so we'll continue our discussions in the next tutorial session. And we'll also have an extra sessions, and yeah, so let's wind up the session for today. Yeah, bye. Plus B vector. So this is our balance of linear momentum equation.
Yeah.
isn't it? Balance of linear momentum. Now what we do is, as we had discussed last time, that and then throughout this lecture we deal only with static problems. So this is
0.
yeah. And when we actually talk about dynamic formulation, we just have to have our even variations, uh, not the variations. We'll have to use something known as a double integration. So like what we have here is right that what we do now, if it's static formulation, then we only need to worry about divergence of sigma plus b vector is equal to 0, isn't it? And then what we'll do is we'll multiply both sides, both sides by not multiply, actually it's taking dot product because it's a vector equation, taking dot product on both sides with respect to some delta v vector. Now the thing is delta v vector has certain properties. Actually, we did not talk about this thing last time, right? So we'll just take a slide digression that there are actually some there has to be, even the variation functions, variation functions or just simply say variation to the function, to any function, has to satisfy certain conditions. Actually, we had discussed little bit about that, I believe, more in a. So we were given some function, right? They say this function, and then we say that okay, it has say f of x. This is x1 and this is x2. So x and these are function axis. The values. So say what we have, we said that f1, f at x1 is equal to f1.
Hey, I can't hear you. Network is not working.
Okay. How about now? Because I think that if I change the slide number, it's showing up. The changes.
Yes,
So
now I can see. Now I can hear you and both you.
okay, it's fine, right?
Yeah, it's good, good.
Okay. So what we say is, say given a function f, when we introduce any perturbations to the function or introduce variations to the function, so in that case, this will be f of x plus not f of x. We had talked about this, right? That f of x means function value.
Yeah.
So this is f, and this is f plus epsilon into h. So h is the perturbation, and not just to be more what you call, to get used to it, we'll always denote variations. Variations to be say delta f. So
Okay.
this means that it's a variation to function f. Now what we see is, although after introducing perturbation can, or even from this schematic here, we see that uh, the values change at every point except for x1 and x2. Except at these 2 points, we are allowed to change the value of f by introducing that variation everywhere. So that's because we have fixed the values of the function at both the ends. These are like boundary conditions, or
Yeah.
what you call endpoint conditions. So which means that because of this, variations has to satisfy properties such as that not h, del f at x1 has to be 0 because we cannot allow perturbations at x1. Likewise, f of x2 also has to be 0 just because it has to satisfy the constraints. I hope you got this right. This point.
Yeah, 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 yeah.
Yeah. So this is so which means that even when we take variations, so variation has to satisfy something known as uh, some kinematic conditions. And as we'll see later, kinematic conditions are what we call as the Dirichlet
Great.
conditions.
Okay.
Yeah.
So which means that we cannot arbitrarily take variations to a function. It always has to satisfy certain constraints. If there are constraints, if there are no constraints, then yeah, it's nothing to worry about. I'll just delete this was yeah. So that's what it is. Yeah. So which means that it's right now we are not, since we are not talking about boundary conditions, we did not talk about what are the constraints, but variations has to incorporate all those kinematic conditions if there are any. So likewise, assuming that variation del V has taken those conditions into account. So now all that we need to do is take divergence of sigma plus B vector, take dot product, and this delta V. Here we are considering these are this is actually virtual velocity. So they have I mean the course has this taken in this manner. Otherwise, the thing is when we talk about internal work and all, we actually take variation to the displacement, not velocity. We are just being consistent with our lecture, but ideally
Okay.
what we do is, I mean, in almost every book you'll see that it's always virtual displacement because that's what makes sense, right? That's what leads to work.
Yeah.
Here it becomes more of power. So it's
Yes,
like
correct. That's
virtual
right.
power.
Yeah.
Yeah, that
Yeah.
doesn't have much meaning in this context. And especially since we are dealing with static problems. So I don't know in static problem where does this virtual this velocity come into picture.
Correct.
So yeah. So what we'll do is let's stick to what we think is fine. So it should be virtual displacement. Then it makes sense, isn't it? So let this be virtual displacement delta V. Okay, and then what we do is so this and then integrate over the domain. So in that case, we'll have to use delta U because U implies displacement. So and then integrate over the domain. And this should be in any current configuration. So that's why I'll integrate it over B. B
Okay.
indicates current configuration, and then this is equal to 0. And this is what we call delta W, which is our virtual work.
Work. Mm-hmm.
Yeah, virtual work. Yes. Now you see, now it's dimensionally consistent as well. That it actually means work because
Okay.
of taking virtual displacement. So this is what we call as the virtual work principle.
So virtual
After
displacement as in for the given domain. So we are
ha ha
saying
ha.
that at every each
Yeah,
point inside the inside interior, you will give
yeah,
some like the material points are moving a little bit like perturbed, right? That's what delta U means here, if I'm not wrong. Am I right?
yeah. So which means that
And
we are
at the
allowing. Yeah,
and
I'm
at
just
the
drawing a schematic for you. I mean,
okay.
so what you see
Yeah.
right here. Yeah. So you see right this one. So this on this part we apply U is equal to U naught.
Yeah.
So this is means prescribed displacement
Correct. Correct. It's a boundary
or
condition.
what is, yeah, this is the Dirichlet boundary condition. And this part is some force which is given by traction T. And this part of the segment is uh, say I will apply traction everywhere apart from this, and this segment of this the boundary we call it SU, and this segment we call is ST. And then which means the total surface area is just a union of both these sets. So SU in union with ST. Now what we see is when we take delta U, right? So delta U has certain things to satisfy. And the first thing that you satisfy is that delta U has to be 0 on, or let's use all those mathematical symbols, right? For all X is an element of SU.
Okay.
So this is the requirement on delta V, I mean delta U. The delta U cannot be chosen arbitrarily. It has to satisfy some relation, I mean some condition. So this is the condition. Now what we say is, so this is the what we call the statement of our virtual work in continuum what we call framework, isn't it? So this is what we do. Had we taken even a dynamic problem, we would still have multiplied it using just virtual displacement. And the thing is, this part, this is actually independent of time. Even if it were a dynamic problem, the variation would still be independent of time, because that's how we select it. Because virtual does not take place, isn't it? It does not take place actually in real world. So this is more of a mathematical imagination, so to speak, isn't it? So, and that's
Yeah,
the reason
I
that we
understood
are,
that.
yeah, that's the reason we call it virtual work. Yeah, it's work which is just imaginary. And the thing is, since the body is already in equilibrium, so this part is already zero. So no matter whatever virtual displacement you apply, it does not matter. It will always be zero. So that is the reason why it's zero. Okay, now let's little bit move forward. And then we'll actually keep on jumping through various lectures. We'll just try to have our own story right now.
Yeah.
And then actually the thing is, we'll keep on discussing. The thing is, most of these ideas, right, when we actually need it, we actually go and read it and even discuss it, right, when the time comes. So that's why when I read the lectures, all the derivations, I just okay, go through the steps. I see, okay, I have understood the step. I will not go into the actually final details. I'll just look at the steps, because unless we are actually working on that, it does not make. I mean, we already know tensor and tensor calculus, isn't it? How the operations work. So it's tensor analysis is more of a practice thing, isn't it? Practice, and then the more we practice, the more we get used to operations. What to which one, what doing what will give us what result and all, isn't it? So okay, so now what we do is, so I'll rewrite the expression here. So it's delta W, and okay, so I must tell you that I really get very this one. I mean, I find it inconsistent that why the lecturer has used
Okay.
this virtual what you
No,
call
no. The point
velocity.
is,
Uh,
it is obvious for you. Obvious as in like you're like biased, but he might have followed the book.
exactly. Yeah,
Book
that's
says
what.
that,
Yeah.
and just following the book, just simply follow the book. You don't know, like you have to be clear about what you're. That's the problem. Yeah.
Okay. So because the thing is, his derivations will always assumes virtual displacement, velocity, right?
No, I
So what
understood.
I'll do
I
is,
understood.
in this slide, I'll always use take virtual velocity. I'll write, and then because we just it becomes a different paradigm then.
Okay.
So we'll just use virtual velocity everywhere. So in this, when I use virtual, I mean this what you call our virtual work, then we'll have divergence of sigma plus v vector into del v vector, and then integrated over the current domain is equal to 0. Okay, we'll keep it like this. Now what we do is, let's separate both the both these terms here. I have break it down into two integrals and dv. Okay, so what we see is we need to. So there is a relation. Actually, we'll just prove it ourselves. So what does
Okay.
divergence of sigma give? So that's what we need to ask ourselves. So divergence of sigma dot dv, when we write in indicial notation, so divergence of sigma is xj, and sigma, I'll not
IJ.
call it exact. Yeah, let's call it xk maybe, and then sigma ij, ej, so ei, sorry, ei, uh, and then ej, and then have ek. So this is divergence of sigma dot delta v. When the need comes, we'll just expand it. And then what we have here is,
So delta V is a vector, or is that what? Is it like?
yeah, it's a vector. It's a vector. Yeah,
Okay, okay.
it's a, it's a
It has
vector.
to be right. Sorry, yeah, because
Yeah, it has to
you're
be a,
getting a scalar component out.
yeah.
Yeah, yeah. Sorry. Yeah.
So now what we do is, so this is a very, for this, there is a very well-known relation. I mean, as I mean, it's a,
Yeah, this
I
is
mean,
huge. Two,
these are things
two,
which
two
has to,
conical
which have,
deltas, right?
yeah, yeah. So it will be sigma ij and then ei and then ej dot ek. Yeah. So this leads to Kronecker delta. So actually, this is a rule which we have to memorize. So these are just the rules which cannot be deducted
Yeah,
further.
yeah.
Yeah. So what we have is, when we in such operations, what we do is we always have dot product towards that side in which there is in which side there is no this tensor product. So
Mm-hmm.
tensor product is here, right? So which is that element which is associated? So in this case, that this does not, on this side there is no tensor product. So because of it, this side becomes dot. I mean, this is how I keep in memory.
Sure.
Yeah, just a minute. I just.
Can't hear you. Oh, muted. Okay.
Sorry to keep you waiting, Dinesh. Actually,
No worries, no
there was
worries.
a
Yeah.
call from, I mean, one of our very senior friend. Like he is a part-time PhD from IIT Kanpur,
Oh wow. Okay.
and he is a scientist, principal scientist at NAL in CFD division.
Good.
He is also from Andhra, yeah. Jyoti Kumar Puttam. So actually, he called me. So I was. It's like not usual time, right? So I thought maybe
Mm.
there must be some emergency there.
No, no, no worries, man. Don't have to. Yeah.
Yeah. Okay. So yeah, the thing is this. I'll just tell you that trick. Actually, this trick. I mean, I have been following since once I tried to learn. I mean, how to remember this. So how I remember it is like this. So there is a tensor product here, right?
Mm-hmm.
So what you do is you always take dot product in the opposite direction. So you have a tensor product here, and there is no symbol between these two. I mean, there is, I mean, nothing explicitly written, no explicit operation going on. So this side, I just take it to be dot product. So this, for then it comes to be EI, EJ dot EK.
Yeah.
So that's how I remember it. I don't know. I don't know whether it is
No, that
is useful, but I believe
is
that.
easy.
And then if you take the other way, right? Other way, which is this way, then you see that this side is nothing is, I mean, nothing explicitly is being acted upon. So you just take it to be EK dot EI and then EJ. Done. So this is how I mean, yeah, I have not found a better way than this to remember it. So yeah, okay. So coming back here, so what we'll do is, so this is delta JK. So delta JK. So which means that delta JK will just replace this K by J, right? From the substitution property. Why to write everything? So let's just uh, have everything in one place. Then divergence V. Now what we can do, right, is that we'll have sigma ij by xj, and then ei dot, and then this also we can expand. Just call it v k, yeah, vk and ek, isn't it? So all we'll have is after dot product will be delta vk and ei dot ek.
Yeah.
Have this becomes I. Now you see, right? So there is a two Einstein summation going on, one over
Yeah.
I
Yeah.
and one over J. And over J gives us the divergence along a particular I. And then we actually perform that for every I. Now, how do we reconcile this is, you see something that I is coming on right hand side. I mean, of this. So the term containing I comes on the right hand side. However, when we take a look here, for sigma, ij is on the I is on the left hand side, isn't it? So this
Yeah.
I will only be summed if there is something from this side.
Okay.
However, we always want delta V to be on the right hand side because that helps us later. So what we do is, why don't we have something like this? Take it to be sigma Ji transpose,
Yeah.
isn't it? So that is the trick here. So take it to be sigma Ji transpose. Now you see that I is on the same side.
Okay.
So we will fix one I, take the partial derivative with respect to xj, and then plus another I, do the same. So so total it has actually 3 cross 3. So 3 cross 3 terms are here.
Okay.
Now what we do is, now I'll say fine, but what are we attempting to do? The thing is we are not, I mean, our goal is to have something that we can also write this as sigma Ji transpose delta Vi minus xj sigma Ji transpose. No, so this will be minus sigma ji transpose, and then partial of del vi by del xj. This from just from the chain rule, right? Look at this here. So it's like when we do say something like d by dx of uv
Yeah, I can see
into,
that.
isn't it? Yeah. So I'll just write in something which is more understand. I mean,
Since it is
I'm sure it takes.
virtual, so since it's virtual, though it is constant and it goes to zero. Is that the principle you're trying to do?
No, no. Let me. So actually, it's just a mathematical, just what do you call it, trickery.
It's
So
tricky,
this
but
is what
some.
we are trying to do. Uh, this is
Yeah,
what we are
okay, okay.
trying to
Yeah,
do.
understood, understood,
This
understood.
operation.
Yeah.
Yeah. Just yeah, the thing is, and if you ask me why are we doing this, the thing is, we'll see that we are able to use the divergence theorem,
Okay.
the Gauss divergence. Now you see, right? Now in the indicial form we have, and then this we can easily write as sigma j ij again. It does not matter. The reason is because sigma is symmetric, isn't it? Sigma ij is equal to sigma ji. It's symmetric. That's what we learned from the angular balance moment.
Yes,
I mean,
yes, yes, yes,
so
yes.
because of it doesn't matter. So we can just keep it even sigma ji. No need of writing transpose. And then what we can have is even in the first case, it will be the same thing. Here also we can just write sigma ji. But in tensorial notation, this will actually just be, it will simply be divergence of sigma transpose del v minus sigma. And since the thing is, since this is a scalar quantity, now and then the other term is gradients of something, some vector quantity. So only way to be this to be scalar is when we take double contraction. So it's this. So this double contraction means you are actually summing over two indices, and that gives us a scalar. This is already a scalar,
Mm.
and now even we can do is as we were talking about that sigma transpose is equal to sigma. So this we can just remove this transpose from that row. Now, now what we do is now let's go back to our delta W. We need to just derive this once because that's to get an idea of how things actually work here. And I'll just write that divergence of sigma we had this dot delta V dV uh, plus, yeah, it was plus, yes, plus divergence of, sorry, not divergence, it's just B dot del V and dV, isn't it? And now we'll substitute what we had derived the expression for this, right? So this one was so this one was uh, as we recall here, it's just divergence of sigma and this V dV plus, not plus, minus sigma double contracted with delta of, I mean, gradient of V, again B dV plus B dot dV dV. Now what we see is, look at the first term here. I'm sure, I mean, this is the well-known, we can easily fit into that well-known Gauss divergence theorem, right?
Yeah.
It's so divergence of some vector quantity over the volume. So this
No,
comes
normally,
down
yeah.
to, isn't it? So what we'll do is we'll take partial B indicating surface, and then sigma this a dot n
Normal vector.
ds, isn't
Yes.
it? Now
Yeah.
you'll see, uh, and let's first deal with this equation. Now what there is again another vector property. I mean this tensor property that if you have something of this form, you can have dot sigma transpose n. So it's like if you have A is a tensor, U dot V, this is equal to, and actually this is, yeah, this is equal to U dot A transpose V. And this is just one property of these tensors. So I'm just using that. So A is sigma here, and U is delta V, and V is n. And so, and then this is ds. And recall that, yeah, we had actually used transpose everywhere. Let me still keep it intact just because it helps us to. Let me keep it transpose still. Now what you see is, so sigma transpose, if it's go on this side, it becomes sigma transpose transpose, isn't it? So it is just sigma. And there is something you may recall from the Cauchy stress principle. So the entire that we had discussed long back about Cauchy stress principle, it just says that how traction is related to stress tensor. So this was the rule, right? So T is equal to sigma n. Isn't it? So now the sigma n is equal to T.
Okay.
And the thing is, now you'll clearly see that over the surface, it's only traction which can act, isn't it?
Yeah.
And since A dot B is the same as B dot
Yes.
A, we can just have a T dot del V ds. Now let us look at the other term. So this term says that yeah. So this term says that B and sigma, and yeah, this is the, I mean, so when we, and here we see that this is symmetric, and about this we don't know. However, any vector, sorry, any matrix or any tensor can be broken down into a sum of
Symmetric and asymmetric. Okay.
symmetric and antisymmetric. Exactly, isn't it? So what we'll do is, that's what we'll do. And when you take a look closely, right? So grad of some, I mean, grad of del V means the grad of some variation is equal to variation of the grad. These are very, I mean, this is something we often use, right? You will see that even in when we're deriving Reynolds transport theorem, we are able to exchange derivative and integral sometimes under certain property, under certain conditions. But in this case, this is very much valid always. Maybe it may not be valid in some this theory of relativity and all, but at least in our range it is valid. Yeah.
Okay.
Yeah, usually in those cases, what we call, I mean, there is this length contraction and all this going on, right? So by the time we apply gradient to that variation, that is no longer the same as taking variation to the gradient.
Okay.
Yeah, just so in that case, it may not be valid, but at least in quantum mechanics, this is what is which is always valid. So we will use this now, and I'll rewrite this. So this term becomes B and sigma, and then also you recall something that we had gradient of V is known as something, right? It is, we call it,
Yeah, it's a strain
yeah,
tensor.
it's called velocity gradient. And actually it gives us something something what is called as
Summation of
strain rate tensor.
D plus D transpose, something like that.
Yeah, so it is strain rate tensor, yeah, because we have to look at the dimensions, right? So grad of velocity, which is meter per second, and grad is per meter, so it is per second. So that's what, so we call it either velocity gradient or strain rate tensor.
So if we considered the virtual work due to virtual displacement,
Yeah, yeah,
then we wouldn't have gotten this strain rate
yeah,
tensor.
yeah, 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 yeah. But the thing, the problem, you know what is the, the problem here? What's going on is we are dealing with a static problem.
Okay.
So in a static problem, how does virtual velocity come into place? So
Yeah, that's
that is
true.
like self-defeating, isn't it? It's very contradictory. So had we taken the entire term, all even the dynamic term or the inertial component, then it was agreeable. Okay, fine. There is, I mean, the choice of virtual velocity is meaningful. But here, our equation did not contain time. So why are we multiplying with virtual velocity? So that's what is always bugging me. Yeah. Otherwise, yeah. If it were not the case, then we actually, yeah, then it would be true. This part is true then. Okay. Yeah. So yeah. So in that case, in this case, what will happen is now we can actually break it down into and then this is also called as L tensor. I mean, that's grad of V. So L tensor is broken down into two components, which is D
Transpose. Yeah.
plus W. Yeah. So yeah, actually, yeah, D is the symmetric part, and W is the antisymmetric part or the skew symmetric. So D means the spatial rate of deformation tensor, and W is the spin tensor that we call. And there is a law. I mean, not law. I mean, that's just a rule. And this is del W by del V. That the double contraction of a symmetric tensor with an antisymmetric tensor is 0. So the thing is, we can easily break it down into two sums. I mean, into into two sums. I mean, two this double contractions, right? One with this and one with this. So, however, what we know is that sigma contracted with W is 0. This is just from that it can easily be derived as yeah. Okay. That symmetric tensor with antisymmetric tensor, double contraction with antisymmetric tensor is 0. Okay. So all we are left with is sigma and the symmetric part D, and then you will have EV. And this with this term we don't require to do anything. Now let's write everything in a good shape. So delta W is the internal work done. I mean virtual work done. This is equal to T dot V so this is T dot V over B parts. I mean over partial B, and then this is again over some surface. In the book they call it dA, but I'll just use ds. This is more. And then yeah, plus B dot del V and dV, and then minus sigma double contracted symmetric part is 0. Now what we'll do is in the next slide, let's just change the order. Or the thing is, if we multiply throughout by -1, it does not affect the equation, right? Yeah. Throughout. So in that case, what we'll have is we'll still call it delta W, and then this let's take it to be over B sigma symmetric part, yeah, symmetric part, dV minus T dot del V ds over partial B minus the other one was B dot del V ds over B. Oh, sorry, over B is equal to 0. Now let's break down these components. Let's try to understand every component. What is stress? Is stress external or internal? If I ask you.
Internal.
It's internal, right?
I mean,
so this is
internal.
Yeah.
Yes, internal. Okay.
Yeah. So this part we call it as the internal virtual work.
Okay.
Isn't it? So because this thing is stress is always a reaction to whatever traction or moments that we're applying.
Correct. Yeah.
And this part, if you take under parenthesis, so it will become plus, right? So under a big parenthesis. So this both the terms added. Traction, is traction internal or external?
External.
Isn't it? I mean, for the way we are looking it, because here parcel B is the outer is the covering of the body. So in this case, traction happens to be external. And what about B vector?
B is a body force, no?
Yeah. So B is also
external.
isn't it? So actually, this becomes virtual work. I mean, this is external virtual work. So when we write it in compact form, so it is W int and this is W del W ext. So when we write delta W is equal to 0, this simply means that W int is equal to W ext. So this is effectively the virtual work principle that we talk about in solid mechanics. When we were dealing with that strength of materials, right? In this case, in that case we were always dealing with some discrete what do you call? I mean, discrete system, isn't it? We are taking a truss. Recall? I mean, we had some truss with rollers, and then provided that it's statically determinate. So in that case, what we used to do is, given some force P, we were actually wanting to find the displacement of at this point. Isn't it some displacement? And isn't it just we're just trying to find the vertical displacement. Now what we used to do is okay. So what we used to do is take the internal energy of the entire body, and then that equal to Pu, because Pu is the external work done. Although in that case, the only difference was it was